Welcome once again. In this session, we are going to discuss very important probability density function called as Gaussian or normal PDF. This Gaussian PDF is basically used for statistical analysis of continuous random variable and plays an important role in the field of communication. Practically, in communication, majority of noise observed are Gaussian in nature. Also, these noise are additive in nature, hence called additive Gaussian noise. Now, for any continuous random variable capital X, its Gaussian PDF is shown in figure and expressed mathematically as a function called small f function small x, that is a assigned real value, and it is equals to 1 upon under root 2 pi sigma into e to power minus x minus mu square upon 2 sigma square, where mu is called mean value of random variable x and sigma square is the variance of that random variable. As shown in figure, the Gaussian PDF is a bell-shaped function having peak value at x equals to mu x, which correspond to the mean value of random variable x. Also, above and below this mean value, Gaussian PDF get reduces and shows even symmetry called as variance or spreading with respect to x. And here the variance is given by sigma square. Now, in order to determine the probability of occurrence of random variable x between any two real values x1 and x2, we have to find the area under the curve within limits x1 and x2, that is shown by the shaded area. So with the help of Gaussian PDF, we can analyze the noise performance in communication system. Next, we summarize all the characteristics of Gaussian PDF. First is, Gaussian PDF is bell-shaped function with peak value corresponding to the mean value mu. Next is, Gaussian PDF show even symmetry so that the probability of obtaining x above and below the mean value is just half. So, probability of observing x less than or equals to mu is equals to probability of observing x greater than mu, and its value is half. Fourth point is, the area under the Gaussian PDF is unity. So, function of x into dx is equals to 1. And the last point is, the probability of finding random variable x between x1 and x2 can be obtained after finding the area of the shaded portion. And this is obtained by integrating Gaussian PDF function, that is small function x between limits x1 and x2, and integrate with respect to dx. So, probability of observing x less than or equals to x2 and greater than x1 is equals to integration of Gaussian PDF taking limit x1 to x2. And in place of Gaussian PDF, that is small f function x equals to 1 upon under root 2 pi sigma into e to power minus x minus mu whole square upon 2 sigma square into dx. Here we take a limit from x1 to x2. Also, here mu is called mean and sigma square is called variance of Gaussian PDF. Next, we talk about cumulative distribution function of normalized Gaussian random variable. Let us consider random variable capital X that is treated as Gaussian, and the Gaussian CDF can recovered from Gaussian PDF using formula capital F function small x equals to integration of Gaussian PDF with respect to dx and taking limit from minus infinity to x. Here capital F function is called Gaussian CDF and small f function is called Gaussian PDF. Here Gaussian PDF expressed as small f function small x equals to 1 upon root 2 pi sigma into e to power minus x minus mu whole square upon 2 sigma square. Here mu is called mean and sigma square is called variance. So in the formula of CDF we can put the expression of Gaussian PDF. Now in order to solve this integration we simply put mu minus x upon sigma root 2 equals to y. and after differentiation on both sides we get minus dx upon sigma root 2 equals to dy. Here, as the mean mu is independent of small x, so its differentiation is 0, and we get dx equals to minus sigma root 2 into dy. Also, for limits, as x tends to minus infinity, the value of y equals to plus infinity, and when x tends to x, the value of y is mu minus x upon sigma root 2. So after converting limits from small x to another real value small y and put dx equals to minus sigma root 2 into dy, we get expression, that is capital F function small x equals to integration of 1 upon under root 2 pi sigma into e to power minus y square into minus sigma root 2 into dy. Here the limits is from infinity to mu minus x upon sigma root 2. And after simplification we get capital F function x equals to minus 1 upon root pi integration e to power minus y square into dy. Here root 2 and sigma is cancelled and limits are same. Now next we further change the limit of integration as there is a negative sign, and after this we multiply and divide by 2 to make it a standard form called a complementary error function. This complementary error function is denoted by ERFC, that is complementary error function, and this is a function of lower limit of integration. So the Gaussian CDF can be represented in terms of complementary error function. This error function is widely used for statistical analysis of noise performance in digital communication system. Also, CDF function called capital F function x is equals to 1 upon 2 complementary error function of mu minus x upon sigma root 2. Now we note a point. Complementary error function behave as a complementary decreasing function. Here, as the value of x increases, the complementary error function decreases. Next, we discuss a special case of Gaussian random variable in which we take 0 mean value and variance of unity. So the Gaussian PDF become small f function x equals to 1 upon under root 2 pi into e to power minus x square by 2. This is also called as normal PDF. So in this special case, the peak of this bell-shaped function is at x equals to 0 and get reduced below and above this mean position called variance, and this exhibit an even symmetry. Now with the help of Gaussian PDF with 0 mean and unit variance as shown in figure, we can represent Gaussian CDF denoted by capital F function, and it is equals to 1 upon under root 2 pi integration of e to power minus x square by 2 into dx. Here we take a limit from minus infinity to small x, or simply we can say that the Gaussian CDF is integration of Gaussian PDF taking limit from minus infinity to small x. But this integration cannot be evaluated as it doesn't give a finite result. So we will introduce a new function which gives a finite result and can be used for noise performance in digital communication system.